Hi, I'm Jamie from Chegg Tutors. Today I want to talk to you about how to solve dilution problems. Problems where you have one solution, you want to form another solution of a different concentration, and you do that through dilution. Now, why would you want to dilute something in the first place? A lot of reasons. In, say, cooking, you might want to decrease the flavor of something if it's really intense. Say, the concentration of the chemicals that make a pepper spicy. In the lab, where you more typically are actually going to do these calculations, because you wouldn't do that in cooking, you're going to want to take, say, a 6 molar solution of hydrochloric acid and make it into a much more dilute, say, half a molar solution that's actually safe for use with students if you're a chemistry teacher or a lab instructor. But then you often have a stock solution that's very much more concentrated than the solutions that you're actually going to use in lab, because that solution can be used to make many different concentrations of solution depending on your needs. But you can't take something less concentrated. It's much more difficult to make it more concentrated. So you want to start with a very concentrated solution as a stock solution in the lab, and then make that a less concentrated solution. And you do that through dilution. And you can calculate a specific, very specific, exact concentration and the volume of solvent that you need to make that concentration through dilution equations. Now, the basic equation or the basic principle behind dilution in terms of calculations is that the amount of solute before is the same as the amount of solute after. We can quantify this in terms of the number of moles of solute. The amount of moles, the moles of solute before, is the same as the moles of solute after. You're not changing the amount of solute, you're simply adding solvent so that you have a less concentrated solution. Let's look at how this figure works out very quantitatively. So in any units, you're going to have the molarity of the initial solution times its volume, is the volume of solvent, or rather of solution, is going to be equal to the molarity of the second solution, the more dilute solution, times the volume of the solvent and the more dilute solution. So even though molarity is in moles per liter, as long as the volume is in the same units, you don't have to actually convert to liters to just determine the volume of solvent needed, or the volume of solvent you need to add. If you are calculating the number of moles of solute, then you really do need to convert to liters, but in general you don't need to, and more commonly you might work in units of milliliters in common lab experiments. Let's look at a specific quantitative example. So if you have 53.4 milliliters of a 1.5 molar solution of hydrochloric acid, and you need a 0.8 molar solution, you need a solution that's about half as concentrated, how many milliliters can you make with what you have, the volume and the molarity that you have? In this case, in this M1V1 equals M2V2, you have M1 and V1, you have M2, the 0.8 molars of solution, and you need the V2, the number of milliliters you can make. So we set this up as an algebraic equation. 0.5 moles per liter, which is the molarity, the initial molarity, times 53.4 milliliters, the amount we have, is equal to 0.8 moles per liter, I didn't write the units here, times x, the number of milliliters. If we solve for this, we get that x is 100 milliliters. We can take 53.4 milliliters of a 1.5 molar solution, and that gets us 100 milliliters, which is a very convenient number, I admit, of a 0.8 molar solution. Now this is a relatively basic problem, and probably the more common problem that you're going to encounter in the lab. You can also use this, however, to mix solutions, say, of hydrogen chloride and an acid, of HCl and another acid, or salt, NaCl and an acid, or whatever, salt and another salt, table salt and another salt. You can always convert to a number of moles and add a certain volume of solvent to perform these dilution calculations. So you might get M1 times V1 equals M2 times V2 plus M3 times V3 if you add a second solute and you keep the same solvent. You're going to get more complex problems like this in certain situations in lab, but you want to master the basic equation, and really you want to master the basic concept before you deal. You don't want to just memorize this equation. You want to realize that this equation comes from the equality of the number of moles of solute on each side of this equation. Because if you are able to remember the principle, you won't need, and you remember the units of molarity and volume and anything you encounter, you'll really be able to derive any of these equations instead of just mechanically memorizing these equations, which runs the risk of you forgetting the equation and then not being able to solve the problem. So it's tempting to just memorize the formula, but you really want to try and remember what this formula represents in terms of a chemical principle, and then you're going to be able to remember the formula no matter what the testing conditions are, and be able to be flexible about the application of this formula. Hope this is helpful. See you next time.